How's it going, guys? Today we're looking at this problem, 153. It's another binary search problem. And basically what we have to do is take our input array, which is in sorted order, and return the minimal or the smallest number in the array. The problem is it's been moved or rotated, so the smallest number is no longer in the first index. So as you can see here, it was rotated 3 times. So one was here, it was moved 1, 2, 3. And as you can see, it's there. The funny thing about this problem is you can actually solve it in one line with this return math.min and spreading the nums in, but I don't think your interviewer is going to accept this solution. So let's go about it in a more logical way. Okay, this problem is really not too bad. We just have to figure out how to execute our binary search. And there's really 3 conditions that are very key to that. So let's go through each one of those conditions along with our algorithm. So the first thing we want to, there's 4 different variables we're going to use in this problem. The first one is the smallest num. That's going to be what we return, and we're going to use math.min throughout this problem to add the smallest number that we currently know of inside of nums. At the default value, we just set it to the first index. So it's our initial guess. It could really be any number. Left is 0, and right is the end of our array, because we're going to do binary search below. And again, we're doing binary search, so we need to use a while loop. While left is smaller or equal to right, we'll carry out these things. So the first condition is if nums is already sorted. So if left is less than right, then we just take the smallest num and we set it equal to left or the current smallest num, and then we just break out of the while loop and return that smallest num. So here's an example. Left is smaller than right. Okay, so we just set the smallest number that we know of, and we break out and return that. Okay, all right. And it's important that we're using left and right to index into our nums array, okay? The next condition is if left is already sorted, all right? So we're going to calculate middle now. Middle is equal to math.floor of left plus right divided by 2. That will give us our middle. In this example, middle is 4, okay? And left, starting from the 0, is nums 0, which is this index, 2. So here's num's middle, 4. Here's num 0, 2. 4 is greater than or equal to 2. Okay, so that means, all right, from this beginning point to the middle point, the nums are in sorted order, okay? It means it has to be in sorted order, right? If this is smaller than this and every number in between it is already sorted, okay, left side is sorted. Let's check to the right now to see if there's any smaller numbers there. And in both these examples, we can see there is a smaller number on the right. So what we do is we change where left is. Left is equal to middle plus 1. And we just carry out our binary search again. Okay, and the last condition we want to check is if middle is smaller than left. Okay, so here's middle, here's left. Okay, huh. 1 is smaller than 4, which means we might be at the start point of our sorted array, but there is a chance in between here and here, left and middle, that there is a smaller value where our sorting begins. So we check for that by moving right equal to middle minus 1, and we carry out binary search again. Time complexity for this problem is log of n for the size of our nums input array. So nums is equal to n. And the reason is binary search eliminates basically half of the searchable areas each time we execute it. Okay? And space complexity is constant because we're only using 4 variables, and those 4 variables are using primitive integer numbers. Okay, so they're just numbers. There's not any complex data structures stored inside of these variables. Okay, let's step through our first example one step at a time. Here is nums in the first example. We set our smallest num to the first index, left to 0, right to the length minus 1 for the last index number. And our while condition is working, so we're going to go ahead and carry out the conditions. we do not hit this first if statement because nums left here is not less than nums right. Okay, so we go on and we calculate our middle. Middle is equal to 0 plus 4 divided by 2 or 2. Okay, so now we're going to set the smallest number to either 3 or 5. And remember, we're indexing in. This is originally set to 3, but we're indexing into our nums array to get that 5. All right, and so we don't change it. Then we go down and we carry out the first if statement, right? Because nums middle is greater than or equal to nums left. Here is middle, 5, and here is left, 3. Okay, so that means we need to do the condition, we need to move our left pointer. So left gets set to middle, all right, plus 1. Middle is 2 plus 1, all right, and that means we go to the next step right here. And in this case, smallest number is still 3. Left is 4. Left is 3. Right is 4. We still meet the while condition. We don't meet this condition. We go to calculate our new middle. Our new middle is 3. Smallest num at, so again, we're going to check indexing into nums at 3. And we do that 0, 1, 2, 3. Oh, it's 1. So we're going to set it to set our smallest num to that value because it's smaller than 3. And then again, middle is greater than or equal to left. 1 is equal to 1. So we move our left pointer to middle plus 1. That brings us to the third step. All right. And now, smallest num is 1. Left is 4. Right is 4. Okay. And while condition is still going to go on because 4 is equal to 4. So we calculate our new middle, which is equal to 4. Smallest num doesn't change. 4 is 2. And 1 is still smaller. And then we're just gonna, again, the condition is nums middle, 2, and nums right, 2, are equal to each other. So we increment left to middle plus 1. And now we can finally stop because left is greater than right, which means we will exit or we will not do our while loop and we'll just return our smallest number, which is 1.